So understanding the normal vector. Now, what is this normal vector? My goal is to try to just give you some intuition to what it is and then how it ties into the equation, actually both of a line and of a plane. So that way you can think about the normal vector and its relationship to those lines and planes. So here on the left-hand side, so you see kind of I have a two-dimensional coordinate system, so you can assume it's x and y. I didn't label it, but the red line that is running through, okay, is basically some line. So, you know, we know that we can write the line in numerous different formats, from slope y-intercept form to the standard form or the scalar form to the parametric, okay, or vector equations of lines. Now, I just want to be able to talk about kind of the scalar form, or at least the kind of standard form of an equation of a line and of a plane. Now, you know that you can have that particular line, so whatever, depending on what this line actually is, although I didn't fully outright it, so we can write it in this way in terms of its standard form, or we can write it where the c actually appears on the other side. Now, they're not the same c, obviously, because if one moves over to the other, then it's going to be negative. Now, the c is actually irrelevant when you're talking about the normal vector, okay, and then what it is. Now, the normal vector, what I would want you to think about as you're looking here on the diagram, is that our normal vector is a vector, so notice that it is a vector right there, and it is pointing, okay, in a particular direction. Now, if you would take that vector, so if I would take this vector and I would shift it on and I would place it on the line. Now, it doesn't matter where on the line it would be, you know, because we can assume that this line is infinite in both directions. But no matter where it's placed, then what you will find is that the normal vector is actually at a 90-degree angle to the line. And that is the main key important kind of aspect of a normal vector. So we designate our normal vectors with typically a small n, okay, and we'll put the little vector symbol on top of it. But the key item is that we have, okay, this 90-degree angle. Now, if you're thinking about the 90-degree angle, you might ask, does the actual magnitude of the normal vector matter? So, you know, could it have been, you know, shorter? The answer is yes. It doesn't really matter. It can be, you know, as big as you want, as small as you want. But the key aspect is that the angle that it creates with the line is 90 degrees. Now, you might also ask, well, I guess it can also be flipped, right? So it can be in this direction. And the answer is also yes. So a normal vector is going to be any vector, and it can be, you know, any other kind of scalar scaled version of its vector, so long as it creates a 90-degree angle. Now, what is interesting is when you do have, I'm going to just keep one of these lines in here so we're not getting confused. When you do have this particular equation of a line, so the standard equation of a line or a scalar equation of a line, whatever you know your teachers call it, or the textbooks you're reading that they call it. I actually personally, I'm not interested in so much in that. But if you do have this form, then what's really neat is that you can get this vector by simply reading out the A and the B components that are in front, so basically the constants that are in front, okay, or the coefficients that are in front of your x and your y. So it turns out that our normal vector, or at least one of the normal vectors, of course, we can scale this line as well. I mean, we can multiply it by 2, you know, we can multiply it by -1, etc. So it doesn't matter so much. We, you know, typically like to have the A being positive as a leading coefficient. But what it is does not matter. We don't always like to have fractions, but they could be. We don't like decimals. But of course, all of those are fair game because they're just scaled versions. Now, this vector, okay, is going to be our normal vector that we have. And that's pretty neat, because if someone does give you the equation of a line in its standard form, then you can just read off what the actual vector would be. So if someone said, you know, this is 2x minus y, let's say, is equal to 5, then you can say, oh, well, the normal vector is just simply 2, negative 1. And that's pretty neat to be able to see that. Now, in the future, you know, you might actually ask, okay, well, why is that the case? Well, there is a reason, because we define these things, okay, in a particular way. But that's not the interest of this video. The interest of this video is just to show you what this normal vector is and give you a few examples. Now, if you expand this and you talk about planes, so obviously in planes in 3 dimensions, well, we don't really want to talk about lines. We can surely talk about a line that we have, but in 3D, we don't have this particular standard representation of a line, right? So our representation, which is now going to get shifted over, so it's going to be now ax plus by plus, you know, that our c now is, okay, is going to be a z component, or a z component, is equal to d. Now this actually creates an actual plane for us. Now, I've talked about this actual plane and standard form of the plane. I'll put up a link up above there for you if you like. Now, do we have the same concept? So, for instance, you know, could we just as easily, you know, read off these and then say that these indeed are actually creating another normal vector? And then what is that normal vector to our plane? Now, this plane that I have, it's really in the, I guess if you think about the x and y axes, okay, in there. So our normal vector indeed would have been a vector, okay, so that we would have, which if you would draw it out, okay, and you would place it anywhere, okay, on this plane, what it would do, we typically kind of put it somewhere in the middle, because of course this plane is infinite, it goes on forever. You know, I just drew it there so that it looks like it's a rectangular surface, okay, that we have. But the main idea is that the normal vector will indeed create a 90-degree angle. And that 90-degree angle, okay, is really kind of cool to be able to have it. Now, it can also be a scaled version of this, right? It doesn't have to be one size. You know, it can be smaller, it can certainly be longer, okay, so we can have that. It can point in the opposite direction, okay, so as long as it's creating a 90-degree, that is considered a normal vector to the plane. And indeed, if you read these out, A, B, and C, it will give you an actual normal vector, which is, again, pretty cool, because you can very quickly figure out, okay, what that normal vector would be. So that's the concept of the normal vector. And it can be any scaled version, so please remember that. The only thing you care about is, does it make a 90-degree with the plane? Now, one thing later on that you'll start thinking about, because you're studying, you know, planes or lines, and you know, the hope is that you've studied kind of the dot product as well. And remember that if you do have a 90-degree between two vectors, so if we took a vector anywhere on the plane, right, which is parallel to the plane, and we take the normal, well, the dot product is going to be equal to 0, and that's going to start hopefully ringing a bell to you where this normal vector actually comes from, and then why, okay, sometimes, you know, some textbooks will call, okay, the standard version kind of a scalar version, because the dot product gives you a scalar output out. Now, of course, it's going to be an equation for us. Now, okay, let me continue, okay, with this concept, because now that we have these normal vectors, you know, what can we do with them? So for instance, sometimes, you know, in textbooks or your teachers on your tests or quizzes, they might actually not just be interested in you understanding what the normal vector is, that it's a 90-degree to a line or maybe to a plane, or honestly to any kind of surface if you wanted to. Now, they might ask you, you know, please construct, let's say, the standard equation or whatever, the scalar equation of a line. So what happens there? Like, how do you do that? How do you go about doing that? So what if somebody gives you the normal vector, right? Is that enough to actually draw out your plane? Well, if we just have the normal vector, as you can see there, it's not enough to be able to say what the plane is, because the plane could be anywhere. And don't forget that this actual normal vector, you know, so as you're doing it, well, technically its tail is at the origin. We just shift it so that we do place it at the plane, right? So it's just kind of shifted or translated somewhere, okay, over. And so having a normal vector is not enough. We also actually need some point so that we can say, all right, well, we have a point on the actual plane. And if we have this point, of course, we can shift this over onto the point, okay, if we wanted to. But if we have a point and we have a normal, we can construct this particular equation of a plane, which is pretty neat. We can also do the same thing with a line. So either or. Now, how do you do that? Well, so let me give you an example. So within here, let's say that we have a normal vector, and I'm going to make it arbitrary. Let's say it's 2. Let's say maybe this is, let's keep it away from 0 just so that it's not too easy for us. Let's say maybe this is minus 2, and then let's say this is 5. So that's my normal vector, right? So it's some vector which is pointing out. And then also, as someone tells us that the point, okay, that the plane kind of crosses through, or at least one of the points, is, let's say maybe it is, the point is 1, 1, and 1. All right, so maybe this is what we have. And now we can actually construct that line. Now, how do we do that? If we know that these are the values of A, B, C, right? So now I've told you that, okay, so that these are the values, so the normal vectors, you can do that. Then you can substitute your point into your equation. So for instance, this is going to be, so now ABC, so it's going to be 2x minus 2y plus 5z is equal to D. Now this D, you know, how do we obtain it? Well, we can substitute the actual point in there. So this is going to be 2 times 1 minus 2 times 1 plus 5 times 1 is equal to D. So, well, 2 minus 2, which is 0, so it's going to be 5. So this is my D. And there you have it. You can substitute it in here, and you have your actual equation of a plane. Now, if it was a line, you could have done the same thing, as long as you know the normal vector, right? That's like if somebody is giving you what the slope is. You can always find what the y-intercept is just by substituting and solving. So that's not a big deal, right? Now, what else can happen in terms of trying to find these equations of the plane, at least these standard equations that we have? Well, what can happen is, or at least what information do you need? Right? If someone gives us a normal, then that's pretty easy, right? And we have a point. Having only a normal is not enough. Having one point is clearly not enough, right? So what else, what might we need? So if you think about that, you know, that's a good exercise for yourself. So sure, I can find the equation of the plane if someone gives me a normal and a point. So that's certainly the case. Now, what else can happen? Now, what about if they give you 2 points, right? So now obviously these 2 particular points, they can't be the same. So 2 distinct points. Is that enough, right? So well, if you go back in here, and if we plotted 2 points in here, and if this indeed was one of them, and then we plotted another one, you know, would that be enough to be able to construct a plane? It's enough to construct a line, right? We know that we can do that. But it's not enough to be able to construct a plane. We do actually need a third point somewhere, right? So now when you're thinking about a third point, you have to be careful because you don't want to take a point and so that the point, okay, actually creates a collinear, right? So they're basically in a line, right? So they're just points that are in a line. So if those 3 points, well, that's useless. That's not going to give us the actual plane. We need 3 points that are going to be non-collinear, and the way you can think about it is that means we need another third point somewhere so that when we're constructing, it's almost like we're going to be creating a triangle. Those 3 points, okay, if someone gives us these will work. Now they are creating, because if we construct it and we fill in, we are actually going to get the surface. So we can certainly have that. So 2 points won't be enough. Unless, you know, maybe somebody also gives us a normal vector or maybe another vector, right? Which is going to be on the actual plane. So there's many varieties, but 2 points won't be enough. Okay, you know, we would actually need a third point, okay, within here. Now, if you do have 3 points, and, you know, let's say, so these 3 points, so they're, you know, constructing some kind of triangle within here, how can we find the equation, right? So because what we need is, well, we need that A, B, C, and we need that D. So we can kind of scratch our heads and say, okay, how do we do that? Well, the way that you can do that, okay, is in the following way. You know, you can take your points, and you know that if you do have 3 points and they're non-collinear, then from any 2 points you can construct a vector, right? So I can construct a vector from one point to another. And then I can construct, you know, other vectors as well. I mean, you know, here's another vector. Now, these 2 vectors that you have, can we find a normal from 2 vectors? Now, what would that mean? So let's say, you know, if here is, okay, so here, if here is one vector, right, this way, here's another vector, okay, in this way, right, that we have, well, we can find, so remember what we need, or what the normal is, or what we're trying to find is, we're trying to find a normal. And if we have a normal, and then if we have 3 points, then obviously a normal, just with 1 point we can construct our actual equation of a plane. But with 2 vectors, so with v1 and v2, and of course we're assuming they're non-collinear, then we can use now the cross product. Because if we take the cross product between any 2 vectors that are on the plane, it's going to give us a 90-degree, right, between those 2, and it's going to create a 90-degree with the actual plane. So 3 points is enough, indeed. We can find 2 vectors from 3 points, so long as they're non-collinear, and then we can use the cross product. If you forgot about the cross product, I'll put a link up above there. And then with that cross product, it's a good to go game. So let's see an example of that. So here is, you know, with 3 points, and we can, you know, pick some points within here. I'm just randomizing these points. I don't want to make them too big or too small, okay, or anything like that. So let's say I have these. Now I do have to be careful, you know, are there actually collinear points? Are they all in a line, okay, or not? Obviously 2 points are going to be collinear. You can create a line out of them. Okay, and then let's, you know, make another one, okay, in here. Let's say maybe this is it. Now, to find if the 3 points will work as you're going through, okay, in here, you know, there's different ways of doing it. You know, you can find, okay, if there is a scalar multiple between them, right? If there is a scalar multiple in between them, then there is these things won't work. Okay, so that's one way of doing it. You know, another way is just, you know, go ahead and try to find your vectors. So I'm going to pick, let's say, you know, this vector and this vector, sorry, this point and this point, create vectors out of them. So I'm going to do 1, 1, 1. I'm going to take the subtraction because that gives me the vector that I need, okay, in between. So this is going to give me, I guess, the vector 1. Let's call this vector v1. So it's going to be 1, 1 minus, this is going to be 2, 1 minus, this is going to be -1. So that's one vector, okay, that I have. And then let's create another vector, okay, so within here. And I'm going to do the same. I'm going to just take one of the points and then subtract. So 2, 1, 3. So now I have another vector. So this is going to be -1, 1 minus 1, 0. And then 1 minus 3 is -2. And now if you look at these 2, so this vector and this vector, you do not want these to be collinear, right? So there shouldn't be a scalar multiple, and it's actually pretty clear that they're not collinear. You can't find, okay, one and the other. So that is, so these 2 will work. So great, they're not in a line, okay, at all. They're not multiples of each other, okay, in any way. And if that is the case, Great, I can now find my normal. So my normal is just the cross product. And in terms of finding the cross product, okay, so what I'll have is, so in the way that kind of I've been taught how to take the cross product in the past, okay, and this is the one that I like, okay, and I pass on to you, is, you know, so let's try to do it. And of course you can look at the link that I provided you if you've forgotten it. So let's take, doesn't matter, right? So I'm going to take this, okay, I'm going to calculate now my cross product to find it. So, you know, let's cross these off. So I'm going to find out what this is. So this is my first component, so 2, right? 2 times, so this is going to be negative, so this is negative 4, 0 times this, so minus is going to be 0, so this is going to be negative 4. Okay, so that's my first component. My second component, so I'm going to cross off this, and within there, now I can't forget that it is negative, okay, of that, because that second component is negative of, and now 1 times negative 2, so that's going to be negative 2, and then minus, okay, negative and negative, which is positive. So this is what I have, so that's going to be negative 3, and the negative, so that's 3. And then here's my last component, okay, within here. So that's 1, 2, so that's 0, 1 minus 0, sorry, 1 times 0, 0, and then that's going to be negative 2, so that's positive 2. And here is my normal vector. All right, so here we go. We found our normal vector. Now, if you're kind of worried, you know, is this really a normal vector or not, you can of course double check for yourself. So meaning you can take this vector, right, and then do the dot product with this vector, and you should get 0, right? So this is what we should get, you know, is that really true? Let's try it. So if I do the dot product in between them, so it's just the multiplication, it's going to be 4 plus 0, and then plus, and that gets 2, 2, so it's going to be negative 4. So indeed, this is 0. And then you can also check it, you know, with this one. Okay, so right there. Now I'm going to leave that up to you. Okay, hopefully I didn't make any arithmetic errors in here. So there you have it. So that's what we have there. So negative 4, 3, and 2. So this is what we have. Now, with this normal vector, I now can construct, right? So what I'll have is now negative 4. This is going to be x plus 3y plus, okay, 2z is equal to d. Now I can take any of the points that I like, so either this one, or this one, substitute it back in. I'll take the 1, 1, 1. So it's going to be 1, so 3. So I'm taking this point and substituting it in. Plus 2 is equal to d, so I can find out what that is. So negative 4, so that's going to be, well, this is 1. So d is equal to 1. There you go. So my equation of the plane, okay, is going to be this, or at least that's one of them, or any scalar multiple of this. So if your teachers or whoever is, you know, teaching you this, if they don't like to have a negative in here, then just multiply this whole thing by negative 1. So meaning 4x minus 3y minus 2z is equal to negative 1. So that's what they want. But it doesn't matter, right? So any scaled version, okay, of this normal vector that we have found will work as long as it creates a 90 degree with the plane. So these were examples of what you can do and how you can find your equations. Now, sometimes, you know, maybe they'll give you a vector in the plane, even better. That way you don't have to find vectors from points. Just remember that the ultimate goal that you want to head to is you need the normal vector somehow, okay, and then you need some other point, right? And how you find it, if it's from 3 points or from multiple vectors, that's up to you. Now, the only annoying part is, obviously, if you are not given the normal, then you have to find the normal, and at some point you're going to have to find the cross product or use some method. I mean, you can use the dot product in multiple ways to find it. I have done that as well in the past. But knowing the cross product is pretty neat. And, you know, don't forget that the direction of the normal vector, you can use your right-hand rule, right? And is it going to point up? Is it going to point down? Like if you want a visual of it. So you can certainly do that for yourself. All right. Okay, so that is it. Okay, with respect to the normal vectors and then how to find your equations, at least of the standard or, you know, scalar equation of the plane. Okay, thanks for watching. We'll see you in a future video. Bye, everybody.